Hi everyone, welcome back to part 2 of the chapter 3 review video. Let's start with number 6 in finding the domain and range for the following relation. So we're given a set of points here, 4 coordinate pairs, and the domain is considered the first coordinate of all of those coordinate pairs. So we've got a -9, we've got 2 4s, and we've got an 8. Those are our domain values. The range values are all of the second coordinates, or the y coordinates of all of those pairs. So that would be 1, 2, and 6. Now the second part of this question is to decide whether or not the relation represents a function, whether the relationship represents a function. The relation is not a function because there are 2 ordered pairs that have 4 as the first element, but then have different second elements. So we have this coordinate pair here, 4, 2, and then we have another one that says 4, 1. So pictorially, and we did this in an earlier example, if I'm comparing the domains to the range values, we've got the domains of 4 and -9 and 8. We've got the range values 1, 2, and 6, and 4 is being mapped both to the value 2 and to the value 1. So because I have a single element in the domain that is being mapped to 2 different elements in the range, by definition, this is not a function. So it is a relation, but it is not a function. Alrighty, so we will move on then with number 7. Let f of x equal the rational expression 2x plus 9 over 9x minus 2, and g of x be the rational expression 6x divided by 9x minus 2. For the given functions f and g, find the following: f plus g and the domain of f plus g, f minus g and the domain of f minus g, f times g and the domain of f times g, and f divided by g and the domain of f divided by g. So to begin with, we want to at least figure out what are the domains of f and g in and of themselves, because their domain values will likely intersect with these different composition functions that we're doing. So let's first just focus on f. F of x is, again, 2x plus 9 over 9x minus 2. And really we're concerned with the values of x that would cause the denominator of this function to be 0. So where might that happen? Where would 9x minus 2 be 0? Well, let's just solve for x here. We add 2 to both sides and divide by 9. And that is going to happen whenever x is 2/9. So in the domain, I want to exclude this rational number because at that point, my function will be 0. So the domain of f will be all real numbers x such that x cannot be 2/9. Any other value is okay in the denominator because that would not cause it to be 0. Now you'll notice that g of x has the exact same denominator. It is also 9x minus 2. So the domain of f is also going to be the domain of g. Okay, so now that we have that in mind, we'll come over to the right here and think about what would f plus g look like. Well, this is notationally the same thing as saying f of x plus g of x. So I'm going to replace both of these function notations with their actual equations, 2x plus 9 over 9x minus 2, and for g, 6x over 9x minus 2. Now these are both rational expressions that have the same denominator, so by definition I can combine them, right? If I have 2 rational expressions with the same denominator, I can write them together by adding the numerators. So I'm going to write 2x plus 9 plus 6 all over 9x minus 2, and then combine like terms. So we've got 9 plus 8x all over 9x minus 2. So another rational expression with the same denominator of 9x minus 2. So whenever you are trying to define the domain of f plus g, essentially what you're going to do is intersect the domain of f with the domain of g. So in this case, since all of these have the same denominator here, the domain of f plus g, domain of f plus g, will also be all values x such that x cannot be equal to 2/9. And so we move on and do the same sort of song and dance for f minus g. This quantity, this notation, f minus g of x, is the same thing as saying f of x minus g of x, in which case we're just going to replace f with its expression 2x plus 9 over 9x minus 2 again, and then we're going to replace g with 6x over 9x minus 2. Now you want to be really careful with this particular setup, because if the numerator of g happens to be itself an expression like a binomial or a trinomial, this negative sign is going to be distributed to all of those values. So just for example, let's say that g of x was like 3x minus 4. You would really just, for the sake of keeping your signs straight and making sure that you're doing the distributive property correctly, you might want to always get in the habit of just putting parentheses around the numerator, because when we're subtracting, that subtraction is not just on the first term, it is also on the second term. So again, that's if the function g has a binomial or a trinomial, or in essence, a polynomial that has more than one term. Put parentheses around it just to make sure that you are kind of holding yourself accountable to that rule. But again, it was 6x, so it's just, subtracting one term here, one monomial. So same denominator, just like in the first part. They both have 9x minus 2, so I can write these two expressions together by subtracting the numerators. So we've got 2x plus 9 minus 6x, and we combine like terms again, and this is going to be 9 minus 4x all over 9x minus 2. Now, the domain, again, just like when we added, the domain of f minus g will be the domain of f intersected with the domain of g. So since both the domain of f and the domain of g were in fact the same thing, the domain of f minus g is, not surprisingly, all values x such that x cannot be equal to 2/9 yet again. And this brings us to a little bit more algebraically involved problems when we multiply functions together and divide functions. So here we're doing f times g. Notationally, we can rewrite this as f of x times g of x. So replacing f with 2x plus 9 over 9x minus 2, and multiplying that by 6x over 9x minus 2. If it is helpful, put parentheses around these expressions, numerator and denominator, so that we do not mess up our distributive property. So in the numerator, I've got 6x being distributed to both 2x and to 9. So we've got 12x squared plus 54x in the numerator. And then in the denominator, do not be fooled, this is a binomial times a binomial. That means that I'm going to have 4 terms in the end by using the FOIL method, and then we'll combine anything that has a like term to it. So first, 9x times 9x is 81x squared. Outside, 9x times negative 2 is negative 18x. Inside negative 2 times 9x again, we've got another negative 18x. And then the last terms, negative 2 times negative 2 is a positive 4. So the inside and the outside terms are both x terms. So we've got two like terms that we can combine here and say that this is 12x squared plus 54x all over 81x squared minus 36x plus 4. Now, just like with addition and subtraction, the domain of f times g is going to be equal to the domain of f intersected with the domain of g. Now, again, since the domain of f and the domain of g are the same and the denominators in the products are both going to have 9x minus 2 and 9x minus 2. Again, we've got all real values of x except that value of 2/9. So we'll say all values x such that x cannot equal 2/9. All right, now the last one is really the trickiest one in terms of figuring out the domain and doing all of the algebra correctly. We want to find f divided by g. So notationally, f over g of x is the same thing as f of x divided by g of x. So we're going to have a ratio or a rational expression divided by another rational expression. So it's going to look like this. We're going to have 2x plus 9 over 9x minus 2 divided by another rational expression, 6x over 9x minus 2. Okay, so maybe we'll put some grouping symbols around it here. This rational expression is being divided by this rational expression. And a little mnemonic device that I tell my students a lot is to do the KFC. So the K here stands for keep the first rational expression just the way that it is. F stands for flip, like flipping from division to multiplication. And the C stands for change, as in change the locations of the numerator and the denominator, make it the reciprocal. So I'm going to rewrite this expression in the following way. I'm going to keep the numerator as it is written, 2x plus 9 over 9x minus 2. I'm going to switch from or flip from division to multiplication, and then I'm going to change the locations of the numerator and denominator for my second ratio. So then it's going to become 9x minus 2 in the numerator and 6x in the denominator. So very convenient that these two f and g functions have the same denominator, because when I multiply by the reciprocal, which is what I'm doing right now, 9x minus 2 is going to cancel 9x minus 2. They're the same expression. So I will end up with 2x plus 9 all over 6x. Now, none of these terms have a common factor. 9 is 3 times 3. 6 is 3 times 2. 2 is just 2 times 1. So I can't take anything out of any more of these terms, and I also cannot reduce those x's because 9 is attached to that 2x. So I cannot reduce something out of a sum. So this is actually as simplified as it can go. But it does present a little bit of an interesting domain for us, because now in my f divided by g setup here, I no longer have 9x minus 2 in the denominator. So you'll see that this is definitely going to affect how I write the domain of this composition. So how exactly do we write it? The domain of f over g consists of all real numbers x for which g of x is not equal to 0 that are also in the domains of both f and g. So how are we writing this? The domain of f over g is equal to all values x such that g of x is not 0, and then also intersected with both the domain of f and intersected with the domain of g. So essentially we consider f, we consider g, and then we consider what we come up with at the end of our division, because obviously I've got a different denominator to consider values of x's that could potentially be problematic. So then we intersect this with the domain of f, and then we intersect it again with the domain of g. So domain of f, domain of g, x could not be 2/9, right? And I can see that in this step right here, when I put f over g, I can see it right here that I still cannot have 2/9. That's going to cause problems in the denominator. And then I've got to consider down here, after I've simplified, what's happening algebraically. Well, I also can't have x being 0 because 6 times 0 is going to be 0. So in total here, my domain is going to be all values x such that x cannot be 2/9 and x cannot be 0. Those two values I want to exclude from the domain. All right, moving on to number 8, the graph of the piecewise defined function is given. Write a definition for the function that best describes the graph. Okay, piecewise defined function. So here I'm going to have two equations, one essentially for talking about this portion of the graph, and then another equation to talk about this portion of the graph. So maybe it'd be simplest to first think about the x values over which each one of these equations would be defined. So I'm going to consider a couple of different things here. Number one, this graph does not have a lower bound, or this portion of the piecewise function does not have a lower bound on x. So it is going to continue forever and forever for all values negative or less than 0. So essentially for x less than or equal to, because notice at the origin I have a filled in circle, so for all values of x less than or equal to 0, I'm going to have one equation. And then I need to define values for this second part of the piecewise defined function over here. Those are going to be specifically for values of x between, it's looking like positive 3 and 0. But notice that at 0, this is an open circle, so I want to have a strict inequality there. And this one is a closed circle, so I want to have like a less than or equal to symbol on the right bound. So for values of x less than or equal to 3 and strictly greater than 0, so not including it, strictly greater than 0 but less than or equal to 3, I'm going to have a second equation. So hopefully the way that we have defined these two things here makes sense to you. Now we'll think about, okay, how do I define those linear values? Both equations are linear functions, so I'll start with this first one to the left that continues off to negative infinity. It is a line, so we're going to use y equals mx plus b to write it. And let's first figure out what the slope is. I'm given the points -2, 2, and the origin. So my slope on this first line is difference of y's, 0 minus 2, over difference of x's, 0 minus -2. So we'll have -2 over 2. That'll be -1. So we've got y equals -1x plus b. And b is representing the point at which we are crossing the y-axis. It's the y-intercept. Well, I definitely know what that point is. It's at 0. So b is equal to 0 for this first line. So my equation for all values of x less than or equal to 0 is just going to be -x. Okay, now I move over to the second part of my piecewise defined function. And it looks like I have 2 points to pick out here. 2, 1, and the point 3, 0. So I can plug those into my equation for y equals mx plus b by solving first for m, difference of y's over difference of x's. So 0 minus 1 over 3 minus 2. We've got -1 over 1 or -1, same slope. So we've got negative 1x plus b. And in this case, it's looking like the line would have passed through the point 0, 3, 0, 3, right about here, 1, 2, 3. And now, even though that particular value is not included in this part of the piecewise defined function, we're getting a general trend for where that equation is going. Just to define the line, I exclude that point right here in the definition by saying, you know, x has to be strictly greater than 0. But I'm going to use the point 0, 3 to finish writing the equation of my line. So in that instance, you know, the y-intercept would have been at b equals 3. So I would have negative 1x plus 3, or negative x plus 3. So that is a great example of a piecewise defined function where I've got to consider different portions of the x-axis and how the function is defined over those different intervals. In number 9, determine algebraically whether each function is even, odd, or neither. And we've got f equals x plus the absolute value of x, g of x is 1 over x squared plus 8, and h of x is the opposite of x cubed over 3x squared minus 9. If you need a quick review, here are our definitions for being even and odd. A function is even if for every number x in its domain, the number negative x, or the opposite of x, is also in the domain. So we do that by essentially replacing all of the x values with, quote, negative x, and seeing if we come up with the exact same function. So let's do that for f. F of the opposite of x would be the opposite of x plus the absolute value of the opposite of x. So the absolute value of the opposite of x is still going to be the same thing as the absolute value of just x. So this will end up being the opposite of x plus the absolute value of x. And this is definitely not equal to f of x. So the function is not even. Now the definition for being odd is that we can replace the number x in the domain with the number the opposite of x and come out with this relation here. F of the opposite of x is equal to the opposite of f of x. So we'll try and do that for f. Maybe we'll switch colors here. And let's check again. So the opposite of f of x, meaning negate everything that defines the function of f. So we're saying the opposite of x plus the absolute value of x. How would that look? This is the opposite of x minus the absolute value of x. Already over here we have the function f of negative x defined here, and so this is the opposite of f of x. Do those two things match? They do not. They have a sign difference right here. So it is not true that this is equal to f of negative x, so we know that it is not odd. It is not even, it is not odd, it is neither. All right, let's try this again for g of x. So we want to check for even, odd, or neither. Even is f of the opposite of x equal to f of x. So let's plug in the opposite of x and see what happens. G of the opposite of x. So 1 over the opposite of x squared plus 8. Well, the opposite of x squared would mean 1 over the opposite of x times the opposite of x plus 8. And negative 1 times negative 1 is a positive 1, so this would be 1 over x squared plus 8, which is in fact g of just x. That's what we started with. So this is an even function. Now, for the sake of argument, maybe you started instead with just finding the opposite of g of x. What would that look like? We would have the opposite of 1 over x squared plus 8, and the opposite is the same thing as basically multiplying by a negative 1. So this would be similar to saying negative 1 over x squared plus 8 in which case this is definitely not the same thing as just 1 over x squared plus 8. So it's definitely not odd, just in case you tried that method first. And last but not least, let's check out h of x, the opposite of x cubed over 3x squared minus 9. So let's first check if it is even. So we're going to check h of the opposite of x. Plug that in. So we've got the opposite of negative x cubed all over 3 times the opposite of x squared minus 9. Alrighty, well, the opposite of x cubed would be negative 1 times the opposite of x times the opposite of x times the opposite of x all over 3. Now the opposite of x squared would mean I would have 2 of those bases. And so simplifying, a negative times a negative times a negative is still going to be negative, but then I'm saying the opposite of a negative, so this will actually end up being a positive x cubed on the top over 3x squared minus 9. Negative x times negative x will be a positive x squared. Now this is not the same thing as just h of x, because the numerator of h of x is the opposite of x cubed. So it is not even. So let's check to see if the opposite of h of x is equal to what we just found for h of negative x. Let's see if they match. So we're going to say the opposite of x cubed over 3x squared minus 9. Okay, well here I basically have a negative times a negative, so this will be x cubed over 3x squared minus 9. And that does match what we found right here for h of the opposite of x. So this is an odd function. So you'll need to be able to use these different properties to decide if a function is even or odd, and then potentially use a theorem that says a function is even if and only if its graph is symmetric with respect to the y-axis, or a function is odd if and only if the graph is symmetric with respect to the origin. Now, last but not least, in number 10, I won't go through, an hour-long video about all the techniques for shifting, compressing, stretching, and reflecting graphs, but I want to show you a publisher-created opportunity that you can use through my math lab. So if we go to the e-textbook for this course and head to the chapter review section on page 273, so right up here in the little navigational window, just hit or type 273 and hit enter. It'll jump directly to the chapter review. It gives a great overview of the different library functions. So I think we called these the parent functions that all of the stretching and the compressing manipulates. So constant functions, identity functions, cubic and quadratic, all of the shifting vertically, horizontally, compressing, stretching, all of them are done to these kind of parent functions. There's a great overview on page 273. And then on the chapter test, which is on page 277, number 10, it has 2 examples there, graphing each function using techniques of shifting, compressing, stretching, and reflecting. Start with the graph of the basic function and then show all of the steps. You'll notice that in the ebook, right next to that number 10, there's a little camera. If you click on that little video camera, it pops up with a lecture video that you can watch those problems being done and manipulated based off of those parent functions. So I thought that was a great resource to use. Or if you just want to use this chapter test prep here on page 277, this is a comprehensive overview of all of the problems from chapter 3, and they all have these little videos next to them. So another great resource from Pearson that you can take advantage of to help prepare for this exam. So again, if you have any questions, let me know, and good luck with chapter 3.